Okay, we're going to do refraction experiments. One that you've actually done similarly in GCSE, but this is looking at the rays themselves. So rather than looking at a light ray shone through, we're going to actually look at where the light is going. So nice and simple, we've got a board and some optics pins. So these are long pins and the board is soft so that we can poke them in. Piece of paper, we've got a semicircular block that's quite useful, and of course a protractor to measure angles. And the aim is we want to be able to find the refractive index, which tells us about the speed of light in this material inside the perspex. So what we're going to do is I'm going to stick in a couple of pins, and I'm going to put them in a line so that they're actually pretty much pointing towards the center. That just makes it convenient when measuring angles, because we're probably going to measure all our angles, hopefully, from this center line here. So if you look through there, you can see the pins on top, above the block, obviously, so there's the top of the block, and you can see the pins through the block. And what we can do is, if we move this around, we can actually see both pins. They're in a slightly different place. So what you have to do is you have to get those two images of the pins to line up. If you got it too far, that's out of parallax, there we go. And if you put it there, then looking through the block, not the ones on top, but looking through the block, those two pins now line up. So what I'm going to do is I am going to, because of where I'm looking from, put two pins in to line up with the pins we can see through the glass. So if we move it ever so slightly to the side, you can see all the pins in a row through the perspex block. I say glass then, but I mean perspex. And likewise there. So when they're all lined up, they're perfectly there. And if we look from above, let me just put that a bit more upright. If we look from above, they are very definitely not at the same angle. Okay, so the ones in the back are coming through this way, and then it's changing direction so that those two are there. So what I'm going to do is I'm going to put some lines on so you can see where this is going. So put the lines on, okay, and you can see that running through. Now, interestingly, what you can see is that the pins above are heading directly towards the center, and so actually we can cheat ever so slightly, because that line, being a radial line straight out there, put something on top of it, means that, there we go, means that I only need to use one pin. So what I'm going to do is, this is line number 1, let's call it that, is I'm actually going to take several pins. So I'm just going to do them at slightly different angles, and the rays will all go straight through. The rays that go past the pins will go straight through the actual center of the semicircle. So it's a lovely quick way of getting several lines done at the same time. So if we go back down, then what you can do is you might be able to see the line, the blue line on the far side, so that was line 1. But if we move around, okay, a little bit out of focus there, I appreciate, but if we move that around, then what we can do is, as long as we line it up with that center point, so there, for example, a bit closer, then what we can do is we can put the pins that line up with that. So there's the first one, okay. If we go around to the second pin to line up with the center point, that's going to be, just move the tile, so excuse me a second, the second pin is going to line up there. Let me just check that. Yeah, so first pin, second pin, so that's going to go around there, and I don't think we're even going to get to that fourth pin, so let's just try the next one, and again we circle that up. That looks to be around about there. Getting very difficult with this, even with this light, bright light. So those 3 pins in the distance are lining up with 3 in the foreground. Number 1 goes with number 1 here, number 2 goes with number 2 here, and number 3 comes to this one. Okay, so I'm going to draw some lines on, and again we can measure some angles. Okay, so there's our angles. Here we have our incident rays coming in, and first one, second one, third one, fourth one, coming out at the bottom, your refracted rays symbol there. So 1, 2, 3, 4. Number 4 is, I suspect, a bit dodgy, so let's just check that before we do our measurements. Or we'll find out when we do our measurements. So if I cheat ever so slightly, I don't know if you realised this when you did this at school, but you need to measure your angles from the incident ray. This is at 90 degrees to the surface, so the normal ray, as it's called. And that line normal to the surface means that if I put the protractor at 90 degrees, then what I can do is I can actually read from my normal line, the 0 line, directly. So what I've got for my angles, I'm just going to put a little mark here, a little table. So I've got angle I, angle R. The first one will be, to me, looks like 21. The second one, 29.5, etc. So we can read them off. So 21 dead on, 29.5, we got 45.5, and the last one is, yeah, it's not 60, so 59.5. Meanwhile, angles emerging from the surface, refracted by that surface, again, make sure 90 degree line is on the surface, normal here. So we have our angles which are 29 degrees, okay, so 29.0. The next one is 43.0. We've got round here, looks like 76.5, 76.5, and the last one, I say the suspect one, I think, is going to be 82.5. I think nearer 82, so let's just make that 82, and as I say, that's going to be suspect anyway. So there's our data. Now, the angle inside is much smaller, so this is going to be the one in the material. Okay, that's the angle within the material itself. Whereas this one is the one in air. Okay, now normally you're thinking of air going into glass, going into water, going into perspex. We've done it coming the other way through. Okay, so that data can go into a graph. If you're plotting sine of I against sine of R, you can work it out. However, in the data book is an easier one, and what we're going to do is from this we can calculate the refractive index of the material. So what we're going to do is use that equation where nu1 is the refractive index of the material, sine of the angle in the material, that's going to equal nu2, refractive index of air, times by the sine of the angle in air. And for our intents and purposes, we'll say that equals 1.0. That's going to be roughly right. So refractive index of air is pretty much the same as a vacuum. So if that is 1, for each of these, calculate the unknown, and then if you average them, because they should all give you the same value for refractive index. But have a look at that. That one, as I say, is, I suspect, going to be very suspect. Large uncertainty because it was so difficult to see where it was. Okay, so give that a go, do the calculation, let's find out what refractive index is.